Not mute. There we go. Hello, and welcome to Aggressive Physics. Today is day 26, where we're going to look at the quadratic equation when solving projectile motion problems. Now, yesterday's problems, the most important thing we realize is that if we have a vector at an angle, we need to break the legs of that vector and determine the x and y components of the velocity. That will give us a y and an x velocity initially. And in most problems, that will be the most difficult thing to add to our problem level difficulty. In this case, I want to take it to the next level. Now, the important thing to realize is that the hidden variable yesterday was not just the fact that we had the initial velocities, it was also the fact that we had the object land at the same height it was launched. Now, football, for example, if I kick it off of a tee and it lands on the ground at the other end, well, that means the YD, the displacement in the y direction, was 0. And when we did that, we found that it was easy to solve for the time. We were able to factor out a t and then solve for t using that method. We had two values for t, but because the object started on the ground and ended on the ground, the initial t, one of the roots was 0, and the other root was a positive number. And that gave us a pretty easy solution. Now, most projectiles do not land at the point that they were launched. For example, a baseball player may hit a ball. The ball was launched from, let's say, around their waistline, and then the outfielder catches the ball. Well, the outfielder doesn't typically catch the ball near their waist. They'll raise their glove up in the air and catch it above their head. So the displacement in that case would be a positive, whatever the difference between the batter's waistline and the fielder's outward reach would be. But it's a positive value. So we can't just factor out a t and solve it easily. Instead, what we need to do is go back to the quadratic equation. And if you guys remember, the quadratic equation is negative b plus or minus the square root of b squared minus 4ac over 2a. And we can solve the quadratic equation by hand, which you've probably done in your math classes. And if not, it's a good thing to practice here. It will get you stronger in math. But for those of us who have done it before in math class, maybe you do one or two by hand. But after that, you should stick to using your calculator if you have a quadratic solver on your calculator. Maybe you have a quadratic solver application for a mobile device, or you can find an online quadratic solver as well. What's important to realize is that the quadratic solver's job is only to get you the time. You still need to go through the process of getting all the givens first. And we have 4 variables typically that we need. We need VI, we need A, we need D, and we need T. And for all the horizontal projectile motion problems, VIY was 0. For all the angled projectile motion problems, once you found the components of the hypotenuse, that became your Vx and Vy. 99% of the time, your Ax is 0 and Ay is negative 9.8. And what we do is use the variable or the direction that we have more information about, and we solve time using that. Now, if we have a problem that does not land at the same height, what we can do is use the quadratic equation to solve for t. So in this case, we've added a new layer of difficulty to the problems. First, you have to break the legs to find the components for v. Then you have to do the quadratic equation to get t. And then you're still not done. You have to probably at that point use the time to solve for the displacement in maybe the x or the y direction. Now, what we'll do is a sample problem where we launch a projectile through the air and it lands at a higher position than it started. And when we do that problem, we'll see that it's important to do the quadratic equation with the proper signs. What I like to do is I like to bring all the variables to one side and then set the equation equal to 0. That's the typical format that you did in math class, and I'll stick to that convention here in physics. The t squared term will be your a, the t term will be your b, and the non-t term, or t to the 0 term, will be your c. If you do it by hand, beware of the signs. If you use a quadratic equation solver, also beware of the signs. What you should find is that most problems you'll have a negative value for a t and then a positive value. But some problems you'll have two positive values. The first positive value is typically on the way up, and the second positive value is on the way down. And what we'll usually use is the second one because we want to get the farthest range possible. Now remember, words like range will come up in the problems, and that could be a difficult term if you're not used to it. Range is a fancy way to say how far downfield an object will land. How far will dx be downfield? Just like hang time was how long the object's in the air for the complete path, in this case we have range as a term that will help us decipher what variable we're looking for. So any problem that says what's the range of the projectile, that means find dx. So let's get on to that practice problem now. Thank you. All right, this problem is going to involve a soccer player kicking a ball from an unknown distance away from the goal. And what we're going to do is try to determine what that distance is. They kick the ball at 15 meters per second at an angle of 35 degrees. So what I did immediately, just to save some time, is wrote out my right triangle. I have my 15 as my hypotenuse, my 35 degrees as my angle. I use the cosine and the sine to get x and y for the velocity, the initial velocity. Now, when I do that, I'm going to start with my Givens list. And I'm going to have my x, I'm going to have my y variables. Vx, 12.29. Vy, 8.6. Ax equals 0. We don't have a rocket on the soccer ball. Ay, negative 9.8 meters per second squared. Now dx is what I'm looking for. dy, however, is not 0 like it's been before, because when the soccer player kicks it, it hits the top of the crossbar. Now in the problem, the crossbar is listed at having a height of 2.44 meters. So the ball has gone up 2.44 meters, positive. I'm going to solve for t, use the t, and solve for dx, like we've done in many of the other problems. I'm going to start with the y because we have the most information. So for the y, it's going to be d equals vit plus 1/2 at squared. 2.44 equals 8.6 meters per second times t plus 1/2 negative 9.8 meters per second squared t squared. Now simplifying this, we have 2.44 here, 8.6 t minus 4.9 t squared. And this looks like it's shaping up to become a quadratic, which it is. So it'll be negative 4.9 t squared plus 8.6 t minus 2.44 equals 0. And you have to do quadratic. And when I did that, I ended up with two roots, 0.356 seconds, and t equals 1.399 seconds. Now both of those are positive roots, and here's the reason. When you're kicking the soccer ball, it could be traveling upward the entire time and hit the crossbar, so it's still on its way up, or it could be traveling so it's on its way down already. So what I'm going to actually do is have to use both t's because we're going to have two possible answers for the distance. So then we're going to say d equals vit plus 1/2 at squared, and this is in the x direction. And I'm going to do that twice. d equals vit plus 1/2 at squared. Now, of course, the a's cancel, so that's going to simplify it. d equals 12.29 meters per second times 0.356 seconds, and then d equals 12.29 meters per second times 1.399 seconds. So we're going to have two answers. So 12.29 times 0.356 equals 4.38 meters away, which is fairly close to the goal. And 12.29 times 1.399 gets me 17.2 meters away. Now both are feasible. You could have a person inside the penalty box kicking the ball and just gets under it a little too much and hits the crossbar that way, so it'll be on its way up still. And you could have maybe a midfielder kick it from past the penalty area and on its way down, and it hits the crossbar that way as well, trying to get it over the goalie's head. So both of these are possible, and since we don't know if the ball was on its way up or down, we don't know which one to choose. So what we would do is say both are possible distances for the player, 4.38 meters or 17.2 meters away.